Welcome to the Explainer. Today, we are diving deep into Amon's AI Journal Primer on Bayes' Theorem. And, okay, I know theorem sounds a bit dry, but trust me, we're going to use this framework to walk through a completely mind-bending statistical puzzle. It's really going to challenge how you process everyday information. Let's jump right in.
So imagine this. You're taking a mandatory screening for a specific drug, and the test is, by all accounts, highly accurate. We're talking 97% sensitive, meaning it catches 97% of actual users, and 95% specific, so it correctly clears 95% of non-users. Now, you take the test, and you get a positive result. So what are the odds you're actually a user? Human intuition just completely screams that the answer has got to be right around 95 or 97%, right? I mean, that just makes logical sense to us.
Well, the real number is 8.9%. Yeah, let that sink in. That is not a typo. Even with a highly accurate test, the true probability that you're actually a Libin user after one single positive result is literally less than 10%. It's a massive, massive gap between our gut intuition and the actual math. So how on earth does a 95% accurate test give us an 8.9% certainty? Well, let's break it down.
To figure out why our brains kind of glitch out here, we have to look at Bayes' Theorem, our hero of the story today. But honestly, it really helps to view it not as some boring, static mathematical equation, but more like a dynamic philosophy. It's this powerful rule of probability that calculates an event's likelihood by gradually updating what we already know as new evidence comes in sequentially. As the source material beautifully puts it, quote, "It is a powerful law of probability that brings in the concept of subjectivity, or degree of belief, into the cold, hard statistical modeling." And I absolutely love that framing. You basically start with a hypothesis, you assign a degree of belief to it based on your own domain expertise, and then, as new data rolls in, you adjust. If the data supports your idea, your probability goes up. If it contradicts it, the probability goes down. It's pretty elegant, right?
And the crazy part is this all started way back in 1763. Reverend Thomas Bayes actually used conditional probability to create the initial algorithm. Then Pierre-Simon Laplace independently formalized it a bit later, around 1774, and again in 1812. But for like 200 years, the heavy computational math kept this logic totally out of the mainstream. Fast forward to today, though, we're seeing an absolute resurgence. Bayesian inference is literally driving modern data science, epidemiology, and the entire global explosion of AI and machine learning systems.
Okay, so let's get into exactly why that drug test math completely broke our intuition a minute ago. This is Section 1, the false positive, understanding the math.
To truly understand that mind-blowing 8.9% shocker, we really need to introduce a concept called the prior. The prior is basically our baseline, our generalized knowledge. According to the data in this scenario, 99.5% of people out there are non-users and only a tiny 0.5% are actual users. This is our starting point. If we just grab a random person out of the general population without doing any testing whatsoever, there's a minuscule 0.5% chance they are actually a user.
So let's run a quick 1,000-person thought experiment. Let's really slow down and walk through this together. Out of 1,000 random people, based on that prior we just talked about, we expect 995 non-users and only 5 actual users. Now remember, our test is 95% specific, meaning it falsely flags 5% of those 995 innocent non-users. That yields roughly 50 false positives. Meanwhile, it correctly flags the 5 real users, giving us 5 true positives. Okay, so the test hands us a grand total of 55 positive results, but only 5 of them are genuine. 5 divided by 55, that is exactly 8.9%. Because the baseline rate of actual users is so incredibly low, the sheer volume of false positives just completely swamps the tiny number of true positives. Pretty wild, right?
This naturally brings us to a huge pivot. If the math is really that dismal in these low prevalence scenarios, how do we fix it? That brings us to Section 2, improving the odds, engineering better tests.
So we essentially have 2 testing metrics to play with here. On one side, we have sensitivity, which is all about correctly catching the positive users. On the other side, we have specificity, which is correctly rejecting the negative non-users. Now, if you're running a lab and you're trying to solve this 8.9% problem, where do you put your R&D money? Most of us would instantly say, well, make the test more sensitive so we don't miss a single user. But the data reveals something totally counterintuitive.
It turns out, all R&D efforts should actually be focused on improving the specificity of the test. Why? Well, because negative examples massively outnumber positive examples in this specific problem. The source data shows us that pushing sensitivity closer to 100% barely even moves the needle. Actually, scratch that. It doesn't really help at all with the false positive flood. The probability response is highly nonlinear when it comes to specificity. Because we have to test so many non-users, pushing specificity to perfection drastically shrinks that giant pool of false positives. And that is what radically improves our actual confidence in a positive result.
But what if we can't instantly invent a physically better test? Turns out Bayesian logic has a built-in mechanism for exactly that. Welcome to Section 3, the superpower, chaining Bayes' rule.
And this right here is where Bayesian inference really shines. It's all about how we leverage that prior knowledge. In our drug screening scenario, we don't necessarily need a flawless physical test. Instead, we just prescribe a second test. But here's the absolute genius part. The posterior probability, meaning the result from the first test, becomes the brand new prior for the second test. That 8.9% isn't our endpoint anymore, it's our starting line for round 2. We aren't testing a random person with a 0.5% general prevalence anymore. No, we are now testing someone who carries an 8.9% prior probability.
Let's walk through this escalation, because it's genuinely thrilling to see the math work. Step 1. The first positive test yields that 8.9% probability. Okay. Now we feed that 8.9% right back into the algorithm as our new prior and administer a second test. If that second test is also positive, boom, our confidence skyrockets to 65.4%. Still need a higher threshold to make a final decision? Absolutely no problem. We just feed that 65.4% back in as the prior and test a third time. Step 3. Another positive result puts our posterior probability at a massive 97.3%. Notice what we did there? We successfully filtered out all that statistical noise without altering the chemistry of the test at all. We just chained our logic.
And that brilliantly illustrates the true overarching power of Bayesian reasoning. It really isn't just about screening drugs or programming AI. It's a profound way of thinking about the entire world. You start with a belief, you measure it against hard evidence, and you iteratively update your worldview. It's like a constant feedback loop for reality. So I'll leave you with this question to ponder today. What previously held beliefs could you update right now by chaining new evidence? Thank you so much for joining me on this explainer. Keep updating those priors, and I'll catch you next time.